Okay, my name is Foti. I come from Italy. I am assistant professor of the University of Messina. My topics are power electronics, electrical machine, and also motor drive. It's working.
Can you try control and N?
It's big enough. Yeah, it was another computer.
Present view in the second column.
Present view. Present.
I don't know the software, but it doesn't have a top.
Right control and
Yeah, I tried, but
it does not work.
no. You want to go like this. It's okay, isn't it?
You have to go.
Maybe you can try to use a lower zoom to fit in this screen.
Lower it too.
Yeah. Lower it.
Yeah, that would
Yeah, I did. Yeah. Okay. Stop. Let's see. Perfect. Okay.
Okay, sorry for this. You can go ahead.
His flexibility needs
Okay, the title of this
Sorry, Salvador, yes.
The title of my presentation is an insulated resonant DC link inverter for single phase photovoltaic generators. This is the outline. First, I will speak about some structures of single phase photovoltaic generators, and then I will show you the proposed resonant DC link with the preliminary simulations, and then finally conclusions. About the structure of single-phase photovoltaic converter, normally up-switching inverters are used to connect photovoltaic strings to the AC grid, but they produce switching losses. We have two types of structure: single-stage structures and two-stage structure. In the second case, we have an additional DC-DC converter that is connected between the photovoltaic string and the full bridge converter. This DC-DC permits to boost the voltage of the photovoltaic panel and also to have isolation, galvanic isolation. In this paper, I propose a new single-stage, single-phase inverters that has the same characteristics, the same advantages of a two-stage converter, because it permits to also boosting the voltage and also to have zero voltage switching. In fact, if we consider the proposed configuration, it consists of a LC resonant circuit, a high frequency transformer with two-step turns radio, and an H-bridge voltage source inverter. The voltage boosting is obtained by switch the tuner step or radio of the transformer, while at zero voltage switching is obtained thanks to the LC resonance. In fact, if we consider this slide, this is the equivalent circuit of this converter, we note that the DC input voltage of the full bridge converter, or H-bridge converter, is not constant as in normally hard switching converter, but is sinusoidal. And the aim of this work is to switch all power devices of the inverter only during the voltage is equal to zero. In this case, we don't have or we have a very low switching losses. And in this equation, we can see that the average value of the DC input of the inverter is N for VPP, where N is the transformation ratio of the transformer. We designed a 60 kilowatt inverter, and we are using 1200 IGBT. So we must set a voltage limit at 1000 volts. This is the peak voltage of the resonant of the sinusoidal waveform. If we consider the total power losses that consists of inverter conduction losses, switching losses, and also the power losses of the LC circuit, we can obtain the value of inductance and capacitance in order to minimize these power losses. It's shown in this picture. About the control system, control system consists of 4 main blocks: sigma delta modulation, proportional resonant controller, MPPT, and hysteresis comparator. Because in comparison with a switching inverter, in this case, it's not possible to implement PWM, conventional PWM modulation, but in this case, we consider sigma delta modulation that consists of varying the density of boost. About the photovoltaic output range voltage is set to a minimum of 200, maximum 400. The peak limit voltage is 1 kilowatt in this case. And the average value of the ceiling voltage is between 315 and 500. So when the voltage of the PV panel, the PV string, is lower than 300 volts, we set transformation ratio NE. For example, during the dark down when the voltage is very low. When the voltage is between 300 and 400, we set the second radio NP. If we see in this slide, we can see that the output voltage is different to that obtained by using PWM modulation. In fact, we have sinusoidal, positive and negative sinusoidal waveform. So by modifying, by regulating the density of a pulse, it's possible to regulate the fundamental components. In order to sustain a continuous oscillation of the voltage and current in LC resonance shell, it's important also to introduce a charging block, because this is the main complication of a resonant circuit, because it's important to don't discharge the capacitor voltage and also the inductance. This is about the simulation. We use the Matter simulator. We are considering 2 parallel strings, 3 in series connected photovoltaic modules. This is some steady state test that's different to radio. In the left, we can see the case of maximum output voltage of the photovoltaic string, 400. With NB as a tone radio, and on the right we can see the case of lower voltage, 200 volts. We can see that the maximum voltage is 1 kilowatt. In this slide, we can see the same condition as the previous slides, but in this case we can see also the sinusoidal, the grid current that is very close to sinusoidal waveform and respect the standards. The regards total harmonic distortion is very low. This is another simulation, another result in MPPT condition. The photovoltaic volt in this case is 377 volts. And also in this case, total harmonic distortion of the grid current is very low. When we change the tune radio, we have a problem, because in the secondary voltage transformer, the voltage has a over voltage. This is due to the energy storage in inductance. For this reason, just before changing the tune radio, we turned off all power switches of the full bridge in order to have a zero load current. And we change the stepper the tune radio during zero current, and we don't have always it's possible to see in the vision on the right that we don't have over voltage. Okay. About the conclusion and future work, So I proposed a single phase resonant DC link for photovoltaic application that permits to achieve zero voltage switching thanks to the resonant LC circuit. This converter has some similar characteristics of a two-stage converter because permits to boost the voltage and to have also galvanic isolation. But in this case, the main advantage is that the increase of the efficiency because we don't have switching losses. About the total harmonic distortion, the standard is respected because the total harmonic distortion is very low. About the future works, we will work about the design of the high frequency transformer and also passive output filter. But the main important test regards experimental test because these are preliminary results on simulation. So we will test experimentally these configurations. In particular in terms of power quality and also efficiency. Okay, thank you so much.
Any questions? Yes, please.
In case of low voltage control, especially low insulation, how do you maintain the AC voltage?
When the PV voltage is very low, the peak voltage of the grid is 325. Okay, so you must synthesize at the output a peak voltage that is higher than this value. Okay, so when the photovoltaic panel voltage is 200, it's impossible. So we use the two radio transformer to increase the voltage. Okay, you must consider that this changing of the tune radio occurs only one time each day, because during the dark, during the day the voltage is higher than 300 volts normally. Okay, during the dark instead you must change the tune radio in order to increase the voltage. That is the same in case of two-stage. Two-stage we have a DC-DC converter. DC-DC converter, if it is also isolated, you have also high frequency transformer, but you have additional power switches, boost converter in this case. Okay, that permits to increase the voltage. But in this case, you don't have additional power switches. You have only LC resonant and high frequency transformer that you have only also in case of two-stage converter.
Thank you. Thank you very much.